Okay. Good morning, everyone. Let's get started. So first of all, we have released homework 4 on Canvas. So again, this homework assignment is quite light. I mean, the workload is quite light. It just asks you to implement SVM. And we know that SVM implementation, no matter it's primal form, dual form, primal is just the SGD, right? And dual form, you just need to call some convex optimization library to do the constraint optimization. So from the programming workload, we do believe this is pretty light. But again, we'll suggest everyone to start early, and because we need you to look at the results and do some kind of analysis and question and answer and so on. Right? So don't try to finish it in 2 hours. That is not very realistic. And also, please feel free to seek for help in office hours. Okay, so let us continue with the kernels and kernel trick. So in the last lecture, we finished the introduction of the dual form of SVM. So basically, there's like a pretty lengthy logic chain about how to derive the dual form. And basically, the idea is to construct a primal form for the dual with the Lagrange function. We'll talk about why this Lagrange, this primal form is equivalent to any general constraint optimization problem, right? And you just switch and min and max, you got dual form. And in for the SVM case, the dual form is equivalent to the primal form, meaning that the optimal solution for the dual is the same as the optimal solution for the primal. Then we can simplify the dual form, right? Because this dual form is a max min optimization problem, right? Is W, and you got some Lagrange function, right? So we can just fix the outer level, the Lagrange multipliers, and then solve the inner minimization problem. We can get some conclusion, right? And we can substitute the results back into the inner level, so we can reduce the problem into just a one level maximization problem. Of course, if you take negative over the objective function, you got the minimization problem. Right? So we also talk about once you have solved the dual problem, how do you recover the optimal model parameters, which include the weight parameter and bias parameter, right? And from the intermediate steps we have derived by solving inner minimization, right? We know that optimal W must be a weighted summation, right? Weighted summation of each training example weighted by the Lagrange multiplier Rn times Yn times Xn, right? And but recover B is not that easy. If you only use the intermediate results when we solve the inner minimization problem, you won't be able to find the optimum B. We must leverage the so-called KKT conditions to help, right? So there's a bunch of derivations and reasoning on that. We do not ask everyone to memorize them, but we do expect everyone to understand the whole logic. Right? It's kind of like lengthy, but it's not hard. Right? So, and then why do we talk about the dual form? Right? The reason that we spend so much time talking about dual form, derive that and solve that, and use a bunch of techniques to recover the B star and W star is that using dual form is a easy and convenient way to convert SVM from linear classifier to a highly nonlinear classifier, right? That goes to the kernel and the kernel tricks, right? So in the last lecture, we talk about okay, if we use the dual form representation of the W star, if you make a prediction, right? If you make a prediction, you see that the classification score essentially is a weighted summation of the inner product between each training input and test input, Okay, so this can be derived by just substitute the representation of W star for W star in the prediction step. You see that, okay? So then if we want to generalize our SVM from a linear classifier to nonlinear classifier, we mentioned that there's one trick. Okay? The trick is that, okay, I first do some nonlinear feature transform over the input feature vector. Right? Say if it is a xi, right? If in the original feature space, the data points represented by xi's are not linearly separable, what should I do? I can invent some nonlinear transform which map xi to some higher dimensional space. Right? We call it feature lifting. Right? And these additional features might come from some nonlinear combinations of the elements in the original feature vector. And we expect that if your feature transformation or mapping or lifting is smart enough, in a higher dimensional space, those data points will be linearly separable by some hyperplane, right? Then, given that assumption, you can imagine in a higher dimensional space, your weight vector can still be represented by the weighted summation of the feature vector. But now the feature vector is the mapped feature vector, is phi xi, right? And then when you do the prediction, when you calculate the dot product between a weight vector and the test examples of feature vector, remember we need to first perform the feature transformation over the original feature vector, right? Then we do the dot product, and then you can derive it. It is still a weighted summation of the dot product between every feature vector training example and the test example, right? But the only difference is that, okay, I need to first perform feature mapping. I first lift the original feature vector for both the training example and the test example into a higher dimensional space. Then in the higher dimensional space, I do the dot product, right? So here motivates us to think about the problem, a computational problem. That is, what if your phi is very, very high dimensional, right? And let us consider an extreme case. Suppose your phi is infinite dimensional. Then in the practice, you will never be able to compute an infinite dimensional vector, right? You won't have such a resource to compute that, right? So then there comes a question like, can we invent or find a function, right, which just calculate this function of x and z in the original feature space, but the result is equivalent to first performing feature mapping over x and z, and then do the dot product in the mapped feature space. If we can find such a function, right, and then we never need to really, explicitly compute the feature mapping and do a dot product, right? I can just compute this function very cheaply in the original feature space. Then I can address the computational issue, right? So that's the so-called kernel trick, right? So to give an example, to show that how this computational trick is useful, right? So we consider a particular feature mapping. We call it quadratic polynomial feature mapping. Suppose in the original feature space, my feature vector has dimension n. That means I have n features. And now I want to construct a mapped feature vector by just enumerate all second order, from zeroth order to second order polynomial terms and combinations about those features, right? If we can take a look, those mapped feature contains like all degree of 0 terms, which are just 1, right? And all degree of 1 terms, which is just x1, x2 to xn, the original feature, right? And then all degree of 2 terms, that is just the pairized combinations of all possible features, right? So if you look at what is the dimension of the mapped feature vector, all degree 1 terms just take 1 term, right? All degree 0 terms just take 1 term. All degree 1 term, n, right? And all degree 2 terms, n times n minus 1 divided by 2, right? You just do some pairwise combination, but you do not want to duplicate. Right? So you can see if you add them together, you will see that the mapped feature vector take the length proportional to n squared, right? And your original feature just n-dimensional, right? So you can see that after the feature mapping, actually increase your dimension, representation dimension to n squared, right? And this doesn't sound too bad, but consider like that if your n is just 1,000, like suppose n is just 1,000, then after feature mapping, you got 1,000,000 dimensional feature vector, which is very, very lengthy, right? And in that case, like suppose we want to compute the dot product between the mapped feature vector A here. So imagine that, okay, I first do the feature mapping. Feature mapping, that means I got 1,000,000 computation, right? To construct the 1,000,000 dimensional feature vector. Then I do the inner product. The time complexity is still 1,000,000, right? So in general, like suppose your original feature vector is length n, right? If you explicitly perform feature mapping and do dot product, then the computational complexity is O(n) squared, right? So the complexity grows quadratically along with the length of the original feature vector. That's really costly. But this is just a very simple case, and actually quadratic feature mapping is very cheap feature mapping. If you do like third order polynomial feature mapping or fourth order polynomial feature mapping, you can imagine your mapped feature vector will grow like n cubic, n fourth, n to the power of 4 and to the power of 6, right? That is growing really fast. If you then do the dot product, you can imagine how costly it is, right? Then, okay, so far any question? Everyone is on the same page, right? Then we consider like, okay, can we have some like easier computational method to avoid doing this explicit feature mapping and explicit dot product? Okay. So here we want to come out a kernel function. That is, I define a kernel function as a function of x and z. X and z are just in the original feature space. That is, they're just n-dimensional. Then I calculate ks. First, I do dot product between x and z itself. Here, there's not any feature mapping. You just do the dot product in the original feature space. Then you plus this dot product and take square. So suppose x and z are both n-dimensional, right? So what's the complexity of computing B? What? Yeah, O of n, right? Why? Because x is n-dimensional, z is n-dimensional. Their dot product takes complexity of n, right? You just do some islandwise multiplication between n pairs of elements and add them together, just O(n), right? And just and then do some constant complexity transformation plus 1 takes square, right? So overall, it takes complexity of O(n), right? And then we can conclude that the result of A is equivalent to result B. So remember, A is doing quadratic feature mapping over X and Z separately, and then do the dot product between the mapped feature vector in a high dimensional space. Right? So we know that this complexity is O(n) squared. Right? But if we just compute B, the complexity is just O(n). And then now we claim that, okay, the result of A is actually equivalent to result B, up to a little bit difference in terms of coefficients. But later we see that coefficients doesn't matter because if you do the feature mapping, you actually multiply the mapped feature vector with the weight vector, right? If there's just some scale difference in terms of weights, then you multiply weights by that some corresponding factor. The result will be exactly the same. Right? That's why the coefficients actually do not really matter. In this sense, actually, A is equivalent to B. But we can see a huge difference in terms of the computation complexity. Right? Computation is much, much cheaper now. Now let's see why A is equal to B. Okay. We want to use a concrete example to show how this works. Right? Okay, so we use a two-dimensional feature vector as an example. So suppose X is X1, X2, and Z is Z1, Z2, right? So here's a feature mapping, right? We just collect all degree 0 term, all degree 1 term, all degree 2 terms, right? So it gives you like 1, 2, 3, 4, 6-dimensional feature vector, right? So let's first compute A, right? We know to compute A, we need to first perform explicit feature mapping, right? So we need to map X to phi X, Z to phi Z, right? So phi X here is already there, right? I just do the feature mapping for phi Z, right? Which is just 1, Z1, Z2, Z1 squared, 2 squared, Z1, Z2, right? Now let's just try to compute A, right? A is just the dot product between these two mapped feature vector, right? We know that we just multiply the corresponding pair of elements, just add them together, right? So let's just do it, right? So 1 times 1 plus x1 times z1, right? So x1, z1 plus x2 times z2 plus x1 squared, z1 squared plus x2 squared, z2 squared, and eventually x1, x2, z1, z2. Okay. Any questions so far? It's straightforward, right? You do the feature mapping over x and z, you just do dot product over this two mapped feature vectors. So now let us look at B. So B is not performing any explicit feature mapping, right? It's just to compute 1 over x transpose z and take square, right? So this is 1 over, what is x transpose z? What is x transpose z? Yeah, dot product. Can someone just read the results? What's the result of x transpose z? Yeah, look at here, right? X transpose z is x1 z1 plus x2 z2, right? And then you take square. Right. Now let just review our middle school math, right? We do the expansion of this quadratic expansion of this term, right? So we know that what you need to do is just take the square of individual terms and then plus the cross terms, right? Multiply by 2, right? So square of the individual terms will be 1. 1 square is 1. And x1 z1 square will be x1 square z1 square, right? And x2 z2 square, which just x2 square z2 square. Then we need to add the cross terms, right? The cross term, don't remember, we need to multiply by a factor of 2, right? So it's the 2, 1 x1, 1 times x1 z1, so it's just x1 z1, right? Plus 2, 1 times x2 z2, right? And finally, 2, this term and this term, right? So it's a x1, x2, z1, z2. Okay, any questions so far? Now let us contrast A and B. What do we see? Yeah, except the coefficients for a few terms, the remaining are the same, right? So we can just find the one-to-one correspondence, right? So one here, right? And x1, z1, here you got two x1, z1, right? And actually, it doesn't matter the results. Later we just give a more detailed explanation, right? So x2, z2, you got two x2, z2, right? And x1, x2, z1, z2, you got two x1, x2, z1, z2, right? And the remaining terms are just two square terms. X1 square, z1 square, right? And x2 square, z2 square, x2 square, z2 square. So now we can see that the only difference in the computation of B and A is that, okay, in some terms, you got two, a factor of two in front of those terms. And in A, you don't have a factor of two. But remember, actually, why is this this doesn't matter, right? Remember doing A, right? You're essentially learning a weight vector for this map to feature vector, right? So that means, okay, you're gonna have W1 times this one, W2 times X2, W3 times X3, X2, W4, W5, and W6, right? And here, this guy is only is equivalent to what? It's just like you map a feature vector like x1, x2, x1 square, x2 square, x1, x2, and they just multiply square 2 here, right? Right? Then you multiply with another feature vector. So just to change the feature mapping a very tiny bit. z1 square, z2 square, z1, z2 square root, right? And when you do the dot product, you see that square root 2, the multiplied becomes 2, right? And now you see how this comes from, right? And similarly here, x2, z2, and multiply 2 here, right? Here, multiply here, right? Right? So essentially, B is equivalent to performing the same feature mapping, except that you're going to multiply some mapped feature by a square root of 2, right? But to learn a linear classifier, right? To learn a linear classifier, you got W1, W2, W3, W4, W5, W6, right? So you know that it actually just rescue W2 by a square root of 2, right? You can equivalent to the W2 learned by using 5. So actually, there's no difference, except that you only need to rescue some weight element. That's why we say, okay, actually, computing A is equivalent to computing B. Does this make sense? Any questions so far? Okay, so from this simple calculation, we can see the power of kernel function. Right? So if you can come out with some function which compute everything in the original feature space, but the effect is equivalent to performing some high-dimensional feature mapping and do the dot product, then that computation will save a lot of cost. That's the meaning of the kernel tree, and this is called kernel tree. Okay. So the kernel tree, right? The definition of kernel tree is as follows. So if we can save time and or space by computing the value of this feature mapping dot product of the mapped feature vectors by only performing operations in the original space without an explicit feature transformation, then we say you're applying some kernel trick. Then the question will be, can we just find out a function of two variables, two vectors, and calculate that, and we claim, okay, we are applying kernel trick? Can we do that? Yeah, but this is of course, this is one precondition we need to assume to use kernel trick, right? Otherwise, there's no rationale to use kernel trick, right? And second precondition is that you must ensure that your arbitrarily chosen x and z is really corresponding to some feature mapping, right? Like phi really corresponding to some feature mapping where x and z then do the dot product, right? Not every function of two input vectors can be equivalent to this. You need to make sure this is a valid kernel function. Okay, so now let us look at what is valid kernel function and what is property of kernel function. You will see that actually to construct a valid kernel function is not very easy. There are a bunch of like commonly used kernel function, but the good thing is if we know some functions are kernel function, then by some rules we can compensate some more complex kernel functions. We just need to follow these rules. We do not need to invent everything from scratch. So let's see what are the properties of kernels. So what functions are kernels? Can we use any function k of two input vectors, as we just said? No, right? Because some function, although can also receive like two input vectors and calculate some number, it does not necessarily correspond to some feature vector, feature mapping, right? A function k of x and z is valid kernel if it corresponds to an inner product in some, perhaps infinite dimensional feature space. Then what kind of function can we say is a valid kernel function? In other words, what kind of function can we say, okay, it must correspond to some implicit feature mapping dot product? Here's the general testing condition. So if we can construct the grand matrix over a set of input vectors, actually it's over an arbitrary set of input vectors, and if you can show that this grand matrix is always positive semi-definite, then your function k is a valid kernel function. Right? This is a sufficient condition. If some function by input function, right, can satisfy this condition, you can claim, okay, it is a valid kernel function. Right? So let us look at the detail about this testing condition. So first, we need to review what does it mean for positive semi-definite matrices. Right? So here's the definition I copied from linear algebra book. If we have a symmetric matrix M, and if for any non-zero vector Z, we have this Z transpose MZ is non-negative, then we'll claim that M is positive semi-definite. Right? So you see some book, they will just use the notation that M is no less than 0. This doesn't mean like every element of M must be non-negative. It just means that M is a semi-positive definite. So actually, positive semi-positive definite is a very useful property for many interesting mathematical objects, right? Remember, we talk about convex function, right? If a function is twice differentiable, how can we show that a function is convex? We can show that its hash matrix is a semi-positive definite. Right? So it's a very often used property. Right? And what other properties does a positive semi-definite matrix have? Just want to stimulate your memory of linear algebra. What? Invertibility, well, strictly speaking, when it is positive, definitely you can say it is invertible, right? If it's semi-positive, it still can be low rank. What else? What else properties? What else properties does a symmetric positive semi-definite matrix have? Yeah, remember one very important concept associated with matrix is eigenvalues and eigenvectors, right? And yeah. For a positive semi-definite matrix M, right? All of its eigenvalues are non-negative. Right? That's a very important property, and that's also the basis to prove many mathematical conclusions. Okay. So now let us look at this general condition. They actually called Mercer condition. So first, what is Grand matrix? The Grand matrix is defined on a set of vectors. So suppose I got n vectors. Right? Denote them by x1 to xn. So each xj, like 1 minus j, 1 between j and j is between 1 and n, right? Can be any dimensional. It's not necessary to be n dimensional, just any dimensional. Here, n just denotes the number of vectors in my set S. Right? And then I can compute a Grand matrix, which is of size in my. How can I compute that? I just do the pairwise dot product between those vectors. So J will be x1 transpose x1, x1 transpose x2, x1 transpose x2, right? And similarly, x2 transpose x1, x2 transpose x2, x2 transpose xn. You just write down, right? And until the last row will be xn transpose x1, sorry. Xn transpose x2, xn transpose xn, right? It's n by n matrix. And in general, if you perform a feature mapping over each vector, so your set of vectors will become phi x1 to phi xn, right? Then you just replace each dot product by phi xi transpose, sorry, phi xi transpose phi xj, right? It's similar. Then we claim that this Grand matrix is always a positive semi-definite. Why? Why is this true? Let's try to prove that, right? Let's just do some review work on linear algebra, right? So if you can concatenate your vectors row-wise, right? So if you represent all the n vectors in a matrix, right? I put every row as one vector, right? So I can construct this n by d matrix. D is the dimension of each vector, right? And then it is fairly easy to write G as x transpose. Right? I mean, you can do it by yourself, but if you just write it down, well, okay, maybe I can just write it for you, right? X is like this. X transpose will be x1 to xn, right? And then you do x transpose will be exactly G here, right? I mean, remember, what's the definition of the auto product of the block matrices, right? It's just like this, right? Now we know that G has such a structure. If you want to show that, okay, for any non-zero vector Z, right? If I want to check Z transpose G, Z, we know that G can be represented by X transpose, right? So you just substitute this into here, right? So Z transpose X transpose Z, right? What can we observe? What can we observe here? This is essentially just the dot product between two vectors, right? Between the same vector. So if you write it down, it's X transpose Z transpose X transpose Z, right? So this is a vector, and this is a vector, right? So you see that it's actually a dot product between a vector and itself, which is always non-negative, right? So you can see that the ground matrix, why is this ground matrix is always positive semi-definite, right? It's you can directly show it. So now let's going back to any kernel function candidate. Okay? So imagine that if K really corresponds to some feature mapping and dot product, really correspond to phi X transpose phi Z, right? If it corresponds to that, right? Then that means your ground matrix, every element can be represented or replaced by the kernel function evaluation at the two corresponding feature vectors, right? And then your G function, your G matrix will still be positive semi-definite, right? That's the rationale, right? So if K is really valid, then you should imagine that, okay, no matter how you pick up a set of vectors, okay, I construct such a function G in terms of K. That function, that matrix G should always be positive semi-definite, right? Because K suppose is to perform some feature mapping and do the dot product, right? That leads to our Mercer's condition. Let K and X and Z be a function that maps two n-dimensional vectors to a real number. That means just it is by input function, right? If K is a valid kernel, then for every finite set of x1, x2, and for any choice real values C1, C2, you got this one to be non-negative. What does it mean? It just means for any finite set of vectors, say x1 to xn, if I calculate this matrix K, G in terms of K, it's Kx1, x1, Kx1, x2, Kx1, xn, Kxn, x1, Kxn, x2, Kxn, xn. This is n by n matrix, right? It just tell you this line of thing just tell you G is a positive semi-definite, right? It just means C transpose. If you denote the vector C will be C1, C2 to Cn, right? Just tell you C, G, C transpose, C, G, C. So next. Then Mercer conditions tells us, okay, if this holds, then your K function is really a valid function. It really corresponds to some feature mapping and dot product. Any question so far? Everyone's comfortable? Yep. So this is a like most commonly used way to check if arbitrary function is a valid kernel function, right? But in practice, even showing this is not very easy, okay? Because this condition tells us you need to pick up an arbitrary finite set of inputs, right? the vectors can be arbitrary, and number of vectors can be arbitrary. And you need to always show the corresponding constructed Gram matrix G to be a positive semi-definite. This is actually still non-trivial in many cases. In practice, how can we pick up kernel functions? How can we select kernel functions or even invent new kernel functions? In practice, we will start with some commonly used established kernel functions. So here we're gonna introduce a few of them. Right? So the first type of commonly used kernel function is called polynomial kernel. First, linear kernel. That is, you take the inner product between x, z. You don't do anything. That means the feature mapping is just identity mapping. Right? Just don't do anything. Or you can view it as you do a dot product and then take the power of 1. And in general, you can take the power of d. Then it's called polynomial kernel of degree d. So basically, you take the dot product between x, z and take the power of d. And someone may say, okay, if you take power of d, you kind of like only preserve the order d terms, right? So what if I want to include all the lower order terms? Then you can add a constant c to your dot product and then take power of d. And you can expand this polynomial function. You see that it actually includes all the polynomial feature mapping over x and z elements up to the order of d, including degree 0, degree 1, degree 2, until degree d. So all interactions of order d or lower will be added into the feature mapping. These are all valid kernels, meaning that they satisfy the Mercer's condition we just mentioned. Another commonly used kernel is called Gaussian kernel. Actually, if you read a lot of kernel learning papers, the most common used kernel is this. It's called Gaussian kernel. So what is Gaussian kernel? For compute a Gaussian kernel, we first compute the squared Euclidean distance between the two input vectors, x and z. You take a square and divide by this distance by square distance by c, and take exponential of negative of this ratio. So you can see that it looks like a Gaussian density, right? That's why it's called Gaussian kernel. Sometimes people call it linear basis function kernel. Sometimes people call it square exponential kernel. But yeah, they're the same thing. So you can see that the kernel function value is influenced by the choice of c. So c here is a free parameter, which we call kernel parameter. So you can see that if c is very small, c is 0.0001, right? So imagine that x and z, if there's only a tiny bit difference between x and z, so your square Euclidean distance is non-zero, then you divide by a super small value, and then it becomes very large. Right? You take negative, take exponential, it is approximately 0. So that's why when you take a very small c, your kernel matrix K itself is approximately identity matrix. Because only when x exactly the same as z, this guy will be 0, right? And then you take exponential of 0, it will be just 1, right? So that's why it's approximate identity matrix. However, if you take a very large thing, like c equals to 1000, right? So you can imagine, like, no matter how far away x is from z, right? Their distance is relatively large, but divided by c, it becomes very small. And you take exponential of this negative, a very small value, it will be approximately 1. That's why you pick up very large c, K will be approximately a unit matrix. All items are approximately the same. So you can see that the choice of c has a very large influence on the kernel matrix. In fact, in the kernel learning method, the choice of those hyperparameters, these kernel parameters is very, very important. So here's one interesting question. What does the corresponding feature mapping for the Gaussian kernel? That is, what is the corresponding phi, which by doing dot product between phi x and phi z, it is equivalent to this Gaussian kernel. I will leave it as a exercise for you, right? But it's not required because I can tell you this feature mapping is infinite dimensional. So if you just write down the feature vector, it's infinite long. Right? That's one example showing you that the power of a kernel trick, right? It can compute the dot product after infinite dimensional map to feature vector. It has, yeah. But just tell you it's just infinite dimensional, infinite long vector. No, it's not like that. I mean, if you're interested, you can try to do that. I guess our homework 4 has a bonus question asking you to do that. I mean, feel free, try to do that. You will have some fun. This is just showing you the power of a kernel trick, and I actually just tell you because Gaussian kernel, along with other common use kernels, here we won't introduce in our class. It's called Matern kernel. Right? Matern kernel actually in many cases even perform better than Gaussian kernel. They all correspond to infinite dimensional feature vectors. Of course, you cannot really compute an infinite dimensional feature vector in practice, right? And to compute their dot product, well, you have to leverage the kernel trick. Okay, so now suppose we have a set of existing kernels, right? How can we construct new kernels, right? We don't want to construct the kernel function from scratch, right? We want to leverage some rules. It's like using Legos, right? Building Lego stuff, right? Use basic blocks to composite a very complex kernel thing. So here are some like commonly used rules to construct new kernels. First, if you multiply some valid kernel by a positive constant c, it's still a valid kernel. If you come out a function f, right, any function f, right, if you multiply a kernel k by fx and fx prime, then this new function is still a valid kernel. So you can represent it as a k bar x and x prime, and this k bar is a valid kernel. If you apply a polynomial to a valid kernel, it will still give you a valid kernel. This is kind of like a nested design, right? You you use a one kernel function and you throw the kernel function into a polynomial function, you still obtain a valid kernel. And similarly, if you take exponential of a kernel function, it's still a valid kernel. And you can also construct a kernel from multiple kernel functions. Like if you simply just add two kernel functions together or multiply them together, it will give you a new kernel. So you can see that we have like several simple rules, right? But if you can just combine them together, they'll give you a super complicated kernel built upon existing kernels. And also we can do some explicit feature mapping because feature mapping requires some kind of imagination, right? You might not be able to construct a kernel which is 1 million dimensional, but you might be able to construct feature mapping which is just 3-dimensional or 4-dimensional. And then if you throw your mapped feature vector into another kernel, you still form a valid kernel. Actually, this type of approach has been used to construct the so-called deep kernel. What is deep kernel? Just use phi as a neural network. So you throw some input the input vector x and x prime into a neural network first. Then you through the neural network output into a valid kernel function, you construct the so-called deep kernel. And deep kernel works very well in many applications. And also, if you can find a symmetric positive semi-definite matrix A, then this quadratic form is also valid kernel. X8, X prime is also valid. Okay, so now we have finished up the discussion about properties of kernels. Before we proceed, any questions? Okay, great. So now we need to finish the last piece of our picture, right? How do we combine kernel trick and SVM-DUE to implement this nonlinear SVM? Okay. So going back to our SVM-DUE form, right? After a series of derivation and simplification, we know that solving SVM-DUE form is equivalent to solving this constraint quadratic optimization problem, right? So it's a double summation yi, yg, alpha I, alpha g. Remember, these are just Lagrange multipliers, right? And then xi transpose xj subtracted by the summation of all alpha i's, right? And you need to respect a bunch of constraints over alpha i's. So, and remember here, the form, it tells us, okay, in your objective function, you just need to do a summation of dot product between every pair of the training inputs, right? If we perform some feature mapping and want to do this SVM-DUE learning in a mapped feature space, then we should replace this dot product by phi xi transpose phi xj, right? Does it make sense? Okay, suppose we have come out some, we have invented some feature mapping, right? And if we want to learn an SVM in that mapped feature space, right? If you look at DUE form, it is equivalent to solving the same objective function, except that this dot product should be between mapped feature vectors, right? Which is phi xi transpose phi xj. Now we have just learned what is the kernel trick, right? We know that directly computing this guy might be too expensive, right? I can use a kernel function to compute that instead. That means we can just replace this dot product by the kernel function between x and xj, and that's it. Does it make sense? You can see that there's nothing much change in objective function, except that, okay, previously I need to compute the pairwise dot product, right? Now I just need to compute the pairwise kernel function value. And there's no change in other places, like in terms of how do you optimize it, how do you call your optimization package to solve alpha i's. Nothing changed. So you can see there's one step to convert your linear SVM to nonlinear SVM. Just one step. Any questions so far? Although, how to arrive at a step, we do need a chain of reasoning, a chain of thinking, right? Okay, so once we have learned our nonlinear SVM, where the feature space, where the mapped feature space is determined by your chosen kernel function, right? How do we perform prediction? So if you look at the prediction, we know that in the mapped feature space, given a test input vector x, right, you'll need to compute the classification score, right? That is the dot product between w and the mapped feature vector phi x plus the bias parameter b, right? Of course, we do not want to compute this explicit feature mapping, right? We're going to leverage the result we have used before, right? We know that the optimal w should be a linear combination of the mapped feature vectors in the training set, right? Now just substitute this guy for W star, then compute this guy. We see again, the W star transpose the mapped feature vector for the test feature vector will be just a weighted summation of the dot product between the mapped feature vector for each training example and the mapped feature vector for the test example, right? And again, this guy can be replaced by the kernel function. So you can see that the prediction also doesn't really need to perform feature mapping, and even doesn't really need you to compute W star. And everything is encoded into this kernel function, right? And everything is computed in original feature space. You still compute a function between x and x, right? But the computation implicitly fulfills some kind of high-dimensional feature mapping and dot product, right? Any questions so far? And remember, once we solve the dual problem, right? It is very easy to get W star, but we also need to find B star, right? And our previous method to find B star is to find a optimal alpha G star, which is right between 0 and C, not equal to 0, not equal to C, such that we can find the B star by subtracting YG by the classification score, right? That's previous how we recovered the optimum B. Right? And here, by injecting the kernel trick, we again does not need to compute this dot product, right? W star and phi X trick, right? Because we have already known that this guy can be computed by kernel trick, right? So here, in the mapped feature vector, if you want to recover the optimal B star, we need to compute difference between your label and the dot product between your optimal weight vector and the mapped feature vector for the corresponding feature vector, right? But we know that this guy can be computed by kernel trick. This can be replaced by this, right? So that means when we recover the B star, you don't need to explicitly compute W star as well. You can still use kernel trick. So now we have formed a closed loop, right? So we found a way to optimize our nonlinear SVM in the dual space, right? Nothing is changed except that you're gonna replace the dot product by the kernel function, the objective function. And then in the prediction and in the recover of B, you never need to explicitly compute the weight vector, right? You can use kernel function to do everything. So in this way, we kind of completely transform our SVM from a linear classifier to nonlinear classifier by leveraging the dual form and the kernel trick. Any question?
So it looks like we could finally find B star. Previous one, we have to know what phi is.
No, we do not need to find. No find. Yeah, that's what we discussed. What do we discuss in the last 3 minutes? Okay, let me repeat again, right? So if you want to find the B star, right, you just need to figure out one alpha G star, which is exactly between 0 and C, right? And know that from what we have previously derived, we know that B star will be this one, right? But in mapped feature space, it should be B star will be YJ times W star transpose phi XJ star, right? Phi is the map feature space, right? The key observation is that this dot product never needs to explicit compute it, right? It can be computed in this way, right? Because we know that W star is represented by a weighted combination of the mapped feature vectors, right? And if you substitute into this, right, you got this is essentially a dot product, a weighted combination of the dot product between a mapped feature vector for each training example and for X, right? And then you just replace the dot product by K function by the kernel. That's it, right? And then in this way you can compute B star. This is very important because your question is very good. This is very important because you will be required to implement a nonlinear SVM. So you need to know, okay, how do you get B, right? And once you get B, okay, we can do the prediction, right? The prediction is simply here. Okay, any question? Any other question? Okay, so and finally we want to showcase what does a nonlinear SVM look like, right? So here's one example. Like this is positive and negative examples in our original feature space, which is two-dimensional feature space. They're not linearly separable. And here we use Gaussian kernel. If you use Gaussian kernel, you can imagine that after you map each point here, blue and red, to an infinite dimensional space, they are linearly separable. But that hyperplane, you cannot imagine, right? You can imagine that, okay, this is your hyperplane, W transpose Vx plus B equals to 0, right? If you project this hyperplane into the two-dimensional space, it won't be a hyperplane anymore because phi here is nonlinear. It will be some curves. That's why we show here is some curves here. Like we show the level sets means that what if I have a hyperplane, not hyperplane? What if I have a W transpose phi x plus B equals to R? Okay. So if you look at the curves which represent this equation, they're nonlinear curve. It's not a linear curve. Why? Because phi is nonlinear. Okay. And where is the support vectors? You can see here. Okay. They're inside the nonlinear margin. This is just to give you a sense, like what does a nonlinear SVM look like, and where do the separation margin, separating hyperplane look like? Where do the support vectors stay? In the original space, it will show as a nonlinear shape rather than a linear shape. It only shows a linear in the original, in the mapped feature space, which you cannot imagine because the mapped feature space is a infinite dimension. Okay. Okay. So now we have finished our introduction about support vector machines. We spent a lot of time talking about what is dual form of SVM. Actually, the dual form is one key component of SVM because the dual form enables us to inject the so-called kernel trick and can smoothly transit your SVM to a nonlinear classifier. And because the diversity of kernel function choices, it actually dramatically boosts the capability of SVM. That's also the most often how SVM is used. SVM is really trained in a primal form. In most cases, trained in the dual form. And to make the final prediction, we are computing dot product. And the kernel trick is a computational trick to compute dot product in higher dimensional space. Right? And it is straightforwardly applicable to SVM. But we would like to point out that the kernel trick is not only applicable to SVM. It can apply to other linear classifiers as well. For example, perceptron. So you can think about how do we do some kernel perceptron. In our homework, there's one bonus question asking you to do this, right? Feel free to think about that. Okay, any questions so far? Okay, so next we want to introduce a very practical use for technique to select hyperparameters. Because we know that in SVM there's a hyperparameter, right? Which is balanced the regularization term, which encourages large margin, right? And the hinge loss, right? So there's a question, right? In practice, how can we select this hyperparameter, right? So the most commonly used approach is called cross-validation. So what is cross-validation? we have a high demand to choose the best model given the data, right? Each best model, I mean, a model can be determined by the choice of the hyperparameters, right? So, and then suppose you have many choices, different hyperparameters. How do you decide which model is the best? Right? Given that you actually cannot really evaluate what the generalization performance is, right? Because you really cannot compute the expectation of the error under your data sampled from some unknown distribution. Right? You cannot collect infinite amount of data. Right? And what you have is just a finite set of training data. Right? How can you do that? So let us think about SVM. Right? One possible or naive idea would be, okay, why not we just optimize hyperparameter? If you write down the SVM objective, it will be, let me just write down the primal form, right? It will be this half square norm of W plus C times the hinge loss, right? Max 0, 1 minus the function margin. Okay. What if I just minimize this objective function in terms of C? What will happen? We know that previously we just optimized this with respect to W and B, right? But now if I want to determine C, can we just jointly optimize the objective with respect to C? Can we do that? Any thought? Okay, suppose we do that, right? Suppose we're trying to optimize W, B, and C. What will happen? What's the value? What's the optimal value C you will get? No, C is positive. C is non-negative. Yeah. We put a constraint that C must be non-negative, right? So I'm just asking, like, what if I jointly optimize W, B, and non-negative C over this SVM objective? Right? What kind of optimal value for C can we get? Yeah, it will be 0, right? Remember, the hinge loss is always non-negative, right? You want to minimize whole objective. That is, I can simply C equals to 0. Does C equals to 0 sound reasonable? Not reasonable at all, right? Remember, C is a balance, right? Tell you how balanced you can well fit data, and also you want to maximize the margin, right? You want to find the best balance of C to get the tightest generalization error bound, right? That's how SVM is motivated, right? If you simply set C equals to 0, that means they don't care about data fitting. That won't give you good results. So that means you have to will hyperparameter separately, right? You cannot jointly optimize hyperparameter with model parameters together, right? That will lead to some disaster. Then how do we pick up C, right? So suppose we only have one piece of data set, right? So C or other hyperparameters should be evaluated in terms of its influence on the generalization performance. Right? To achieve that, how can we do it? So we're gonna use the so-called k-fold cross-validation. We're gonna split the data in our hand into k equal sized parts. Right? Say it just take k equals to 5. Right? So I have 5 parts of data, right? To evaluate C, right? What do we do, right? So every time we're gonna pick up one part of the data, pick it out as some testing data or validation data. We only train our model with the remaining parts. So for example, in the first step, we're gonna exclude part 5 for training, right? I train my model on part 1 to part 4. Then I test my model on part 5. Then I can evaluate, okay, under some particular choice C, for example, C equals 0.1, right? What is the performance? What is general performance? Right? And of course, doing only the test on one part will not be sufficient. I will just repeatedly do it for 5 times. Each time, it just pick out one part as the testing set. Right? I use the remaining 4 parts for training. Then I test what's the performance on that test set. Right? I go through each of these 5 parts. I got 5 accuracies. Right? I just do the average. And this average serves as the evaluation for using this particular C choice. Right? And then I got evaluation for one choice of C, right? Of course, you might have a set of candidate values for C, right? So you might have 0 0.001, 0 0.01, 0 0.1, 0 0.5, 5, 100, and so on, right? So for every C choice, you just perform this k-fold cross validation to compute an average accuracy, which represents what is the performance of using this particular C choice, right? Then you just look at the performance for every C choice and pick up the one who has the largest, the best measurement. That is called cross validation. So now let us formally define this k-fold cross validation. Right? We first split the data into k equal sized parts, then train a classifier on k minus 1 parts and evaluate the classifier on the remaining one. We repeat this procedure using each of the k parts as the validation set. Then our quality of this particular hyperparameter is evaluated by the average of this k estimates. You got the evaluation for one hyperparameter choice, right? You just enumerate every possible hyperparameter choice and use k-fold cross-validation to get the evaluation. Then pick up the hyperparameter choice with the best one. Suppose from this set C, right? Your best choice of C should be 0.1, right? You're done with your k-fold cross-validation. Now you can safely use C equals 0.1 to train your model on the whole data set. In that case, you won't need to partition the data set anymore. You just leverage the whole data set information with this best C to train your model. This is called cross-validation. Right? Any questions so far? Right. Repeat for every hyperparameter choice, right? So here's the general framework. How do we know what the best hyperparameters are? You evaluate every hyperparameter using cross-validation, right? And then you pick the best according to the cross-validation performance. Then you train on the full data using this setting. Okay. So this is a very simple, very straightforward method, but just be aware it could be computationally expensive, right? So especially when your data set is large, right? So suppose you have like 1 million data points, right? You partition it into 5 folds. Right? That means you have to run 5 times training, and to the average, you can get the performance measurement for one particular hyperparameter value, right? And you have to enumerate every possible hyperparameter value you think is meaningful. And for every possible choice, you have to run your training for 5 times, testing for 5 times to get measurement. This is super expensive. But in general, it works very well. Okay, any questions so far? Okay. And in our homework, we'll ask you to use cross-validation to pick up the best choice of C in our small real-world data set. And we can feel like how this cross-validation, we can get a sense of how this cross-validation help you find to do the model selection. Okay, let's stop here today and see you on Thursday.